Okay, so we are now continuing with starting out with topology. So we've done with what is abstract algebra, some terminology we've introduced in abstract algebra. Now we're going to see about topology. So what is a metric space? So if I have a space like this, which is not your normal Cartesian, doesn't look anything like your, let's say it looks like this, like a folded piece of paper or a bent piece of paper. Okay, now we can call it a metric space if you take 2 points, any 2 points between here, and if those 2 points satisfy the criteria given here. Okay, so this is the distance. Okay, so this is the distance between x and y, and if it satisfies the equalities and the inequalities shown here. Okay, these four conditions. Now your metric space can be divided up into, let's say you are taking intervals, or you're taking subsets, okay, of the metric space, that if you take the union of all of them, you get the entire space. Okay, so we have two terminologies. We have an open, just like you have an open interval and a closed interval, you have a open and a closed set. Okay, so what is it? So generally, if the limit points of the interval are included in the set or the interval, is called a closed interval, right? So if I have 2, 3, 4, and this is the limit points, that is, or the end points, or they are called the limit points. If 1 and 5 are included in your subset, then it's called a closed set or a closed interval. If 1 and 5 are included in the interval, it's called a closed interval. If 1 and 5 are not included, it is called a open interval or a open subset. Okay, so just introducing some terminologies that you might come across. So we'll quickly get to the points that are of interest in current area of physics, already in use. These concepts are already in use. So there are two, here we consider two different topological spaces. Okay, they are topologically equivalent. Okay, we'll see what we mean by that. This is a coffee mug. Okay, think of it as a collapsible coffee mug. Okay, it is made out of material that you can deform. Okay, it is not, let's say it's not hard material that you cannot deform. Think of it as made of collapsible or deformable material. Then it turns out that you can deform that coffee mug into this donut. Okay, you can, if it is made of collapsible material or deformable material, you can deform this coffee mug into a donut. Therefore these two spaces, or these two spaces are called topologically equivalent. The space of a donut, right, and then the space of a coffee mug. Okay, so they are called topologically equivalent. Okay, so these deformations that you can make, okay, these are continuous deformations. They call if they are continuous, what is the condition? So that is what we are going to see. Okay, we said they are continuous deformations. Intuitively it means, what does it mean? That you can squish it, squeeze it, and you can deform it without cutting the material or obstructing the material in cutting and shaping the material. Okay, if it is made out of deformable material, you are allowed to cut it, squeeze it. Okay, that's what it means. But in mathematical terms, how do we define it? You're not allowed to cut it, but you are allowed to deform it. So mathematically, this coffee mug has to be made into this donut. Okay, by some continuous deformation. Okay, deformation, and I'll cut it. So this continuous deformations, in mathematics we use functions, right? If you have a set, right, if you have some values of x, right, you can use a function f which takes it to some new value y, right? So function is a kind of a map, right? So function is a map, and when the map is continuous in topological sense, what it means is you're not cutting the material. So if the map is continuous, then it means that they are topologically equivalent. Okay, and what is the significance of this is there are few topological invariants. Okay, here the topological invariant is a hole. Okay, because here you have a hole in a coffee mug, right? Here you have a hole where the handle is there, right? There's a handle, and when you deform this material, right, the number of holes remain the same. Here in the donut also you have only one hole, right? In the center of the donut you will have a hole, right? So therefore you have topological invariance. Okay, you have these topological spaces. By continuous deformations you can find out the topological invariance. So how do we define this continuity, okay, of map? So in topology a continuous functions is called a map. So in calculus how will we define continuity, right? You know how to define continuity, right? So if, just as I said, if x is some point, right, and you operate f of x on it, right, you will get a new value, right? You will get a new value. So if the interval between x and x naught is small, then the interval between, magnitude of the interval between f of x and f of x naught is also small, or it is, we have, so it is a positive. So the norm of the difference between x and x naught is a positive quantity, then the norm of the difference between f of x and f of x naught also is a positive quantity. Okay, so we've denoted that these are positive quantities. So this is how we define it in terms of in calculus. Okay, and in topology how will you define it? So just as I said, you will come across this terminology in set theory, right? What is an image and a pre-image? So if you have a set X, right, if you have a set of, or a domain and a codomain, you might come across this terminology as well, right? Domain and codomain. So if you have a set X, let's say X, and there is a function that takes it to Y, and let's say 3 is taken to Y, and it becomes 6. So the image of 3 is 6, right? So the image of, so the image of 3 is 6, right? And the pre-image of 6 is 3, right? So this is the terminology that you would have come across in set theory. So every element, right, or every point in Y in the topological space should have a pre-image. That is how you will define continuity in topology. Okay, that is how you will define it in topology. So that means, what does that mean? If there are, these are the elements here, right? These are points here, like say. So each, so this has a pre-image here. This has a pre-image here. This has a pre-image here. Then we can say that F is a continuous deformation. Okay, if F is a continuous deformation, or you have a map between, essentially, from how to get to X to Y, there is, for every point there is a map, right? That is what continuous deformation means. Okay, that is what continuous deformation means, and this way of deforming is called homeomorphism, right? This way of deforming a topological space from one to another is called homeomorphism. And just the language that you would have learned in set theory, right? If the map is one to one, it's isomorphic. Okay, if the map is not necessarily one to one, but there is a map, right? For every element there is a map, but it's not unique, then it comes under a broader category called homomorphism or homeomorphism. Okay, in this case. So that is the terminology that you would have studied in set theory, which continues here in your study in topology also, right? The general idea is the same. Okay, specifically it might be defined slightly differently in different places, but the general idea is the same. So what are the other topological invariants that you might come across? So one is a vertex. So vertex, so three, so here you have you have three edges meeting at a vertex. Okay, so this is a vertex, right? Now the number of, so you can deform this. Okay, so this can be, these edges can be deformed like this, but there is no way to change the number of vertices, right? This is not a this is not a possibility. You cannot change the number of uh, edges here, and you cannot change the number of vertices here. Okay, remember what you are allowed to do. So you are allowed to deform, right? You cannot cut them, you cannot cut it, right? So therefore you can deform. So here you can see a deformation, but the this is not possible, this transformation is not possible. So we've been talking about a hole so far, right? So how do we define a hole mathematically? Okay, so if this was a, let's say this is a donut, my drawing is going to be very poor here. So this is a donut and this is the hole at the center. Okay, this is a hole. Now, if there is a hole, then it means that you cannot deform. If you take a function like this, okay, you cannot shrink it into a hole. Okay, you cannot shrink it to a point, right? If you take a function like this in a space where there is no hole, you can continuously deform it. You can deform it into a hole like this. Sorry, you can deform it into a point like this, right? If you take a if you take a function like this, okay, if you take a function like this in a space where there is no hole, you can shrink it like this, right, first time, then you can shrink it further, you can shrink it further, you can shrink it to a point. But if there is a hole, what will happen? That space you are not allowed to go, because in that topology that space doesn't exist, there is a hole, right? So you cannot shrink it to a point. So that is what we are trying to convey. So some more topological terminologies that you may kind of come across. One is called compactness of the topological space. Compactness just means that the limit points are included. Okay, just like we had studied closed interval, right? So closed interval, closed set. That means in a closed set the limit points are included. So if when we say a space is compact, that means the limit points of the space are also included in the space. That's what compactness means. Then we have a connected property. So this is called the property, connected property of the space. Connected property just means that any 2 points are connected in that space. Okay, so here if you take the space A, you can take a point here. Okay, my drawing is okay, let's, the color of the pen is red. Okay, so I'm not able to draw here. So you can, what you can do is if you take a point, okay, so let's say I'm using a marker now. Okay, so we can take a point here and we can take a point here. These 2 points can be connected in this space, right? Can be connected in this space. Same can be done here. If you take a point here, if you take a point here, these are, you can make a connection between any of the 2 points. So, or it is true that 1, 2, 3, 4, all these spaces are connected. Okay, these are connected spaces. Okay, they are all connected spaces. But if you see the last case, they are a, it is an example for a, not for a space that is not connected. Okay, so if this space, if I take a point here and if I take a point here, let's say I take a point here and I take a point here. Now there is no way to connect these 2 points. Okay, guys, remember this, in this white place the topological space does not exist, right? But if I pick a point in this space, I can connect these 2 points, right? Where the color is, there is a space. Okay, the topological space exists. But here in this space, the green color here, there is a disconnection, right? So there is no way to connect these 2 points that I've picked in this space, right? So this is an example for a space that is not connected. All these 4 are examples for space that are connected, because I take any point here, I can, 2 points I can connect them. Here also same is true here. I can take a point here, I can take a point here, they are connected. Next, another terminology that you'll come across is homotopy of functions. Okay, so homotopy just means if I take a function like this, I can continuously deform it into another function like this. That is what homotopy simply means. So an example here, if I take a function like this, right, this is a circle, right? I can continuously enlarge this circle, right? I can continuously enlarge this circle. So this is the functional form and how the enlargement can be denoted by the functional form I have just given here. Okay, this is the example for homotopy of functions. Now, why is this significant? Because we study something called knot theory in physics. Okay, this so this is actually has this knot theory in mathematics has applications in physics. Okay, now this crisscrossing you see, right? This is a crisscrossing, and when there is a crisscross, we call it a knot, right? What is a knot mathematically? A knot is something mathematical. How we define a knot is, now this crisscrossing, if you can untie this crisscrossing without cutting open this, without cutting it somewhere, okay? Without, if you cut it, okay, you're not allowed to cut it. You're allowed continuous deformation. So here you can take this and you can deform it into something like this, right? You can also deform to something like this. But the number of crisscrossings or the number of knots, if they do not change, right, then if we can call it that if the crisscrossings of the number of knots do not change, right, then this, we can say that is to be a knot. That can be considered to be a knot. Okay. So when you start out with this scenario, you can deform it continuously. You're allowed to deform it how much ever you like without cutting open the string. Okay, without cutting open the string. Now, when you do that, these knots are, you are not able to untie these knots. If you are able to untie the knot without cutting open the string, then it's not called a knot. Okay, then it's not a knot mathematically. But when you do continuous deformations, or when you twist and turn it in real life, okay, there's a knotted situation like this, and you are twisting and turning it, trying to untie it. If you are able to untie it without cutting it open, right, if you're able to untie it without cutting it open, okay, then it's not called a knot, right? Then it's not called a knot if you are able to untie it without cutting it open. But if you have to cut it open to untie that knot, then it's called a knot. Okay, so let me write that out. It is a knot when it can be untied only by cutting open the string. So that's what is called a knot. So there are few polynomials, okay, called Alexander polynomials, Jones polynomials, which encode some properties of these knots. But where are these useful in physics? Now there's a field of physics called topological field theory. Okay. Now a state, a particular, let's say a particular quantum state, is said to be topologically protected when you have a situation where the continuous deformations that you do, okay, the continuous deformations that you do, their continuous deformations are called isotopies. Okay, here. Now, the continuous deformations that you do, if the knot, as we said, a knot is a topological invariant that does not change. Okay, if it is, if there is a knot, okay, if there is a knot in that state and that does not change, then that state that does not change is called topologically protected, because it is a state where by continuous deformations that property of that state does not change. Okay, so that particular state is called topologically protected. Okay, so these are things that you will come across in your physics. Okay, so next I'm just introducing some terminologies that you will come across in differential topology. Okay, so as we said, now this is called a manifold. Okay, and it is going to be called a differentiable manifold when you know this is your Cartesian space, right? So this is just x and y, right? So this is just x and y axis, and this is your simple 90-degree line, right? So this is 90 degrees. But here you cannot impose a Cartesian axis here, right? In this space or in this manifold, it's called a manifold. You cannot impose a Cartesian coordinates, right? You cannot impose Cartesian coordinates to do differentiation and integration on. But that is the case globally. But locally, if you are able to impose Cartesian coordinates, let's say in this small tiny region, you can draw some as you draw something like this, where locally this is a Cartesian space. Okay, locally this is a Cartesian space, but globally it's not. Okay, globally it's something else. Looks totally like something else. But locally in this region alone, if you can impose a Cartesian coordinates to do your integration, to do your differential calculus, then this is called a differentiable manifold. Okay. Now, if you break, so this is, so you can break this entire region into these differentiable manifolds by imposing locally Cartesian spaces. Local Cartesian coordinates you are able to impose, and you are able to do differential calculus. Now, this breakup, okay, this breakup of the space locally, okay, these Cartesian coordinates locally are called charts. Okay, each of them are called charts, and the collection of all of them together is called a atlas. Okay, so a collection of all of them together is called a atlas. Right. Next is another terminology that you might come across. They are called vector bundles. Okay, what is this bundle terminology? So you try to picture what a bundle is in a normal uh, everyday sense that you come across, right? So similarly, that same intuition is preserved when it is applied in mathematics. So a vector bundle So a vector bundle is a topological construction that makes precise the idea of a family of vector spaces parametrized by another space X. So what we are considering, so we'll go from example to then to abstraction. So what we are considering here, these red lines are actually called the tangent bundle. So this is here you can see a circular object. Okay, here you can see a circular object that is some space, that is some, let's consider it as some space. Now this low, at every point we can draw tangents, right? So we can, every point we can draw tangents to this curve, right? Or tangents to this uh, curve where, which is considered on some space. So the collection of all these tangents, right, is going to be called your vector bundle. Okay, or your tangent bundle. Specifically your tangent bundle, generally your vector bundle. That is what they mean. A vector bundle here specifically is a tangent bundle, is a topological construction that makes precise the idea of family of vector space, because here we have a family, right? Because at every point it is the tangent space is something, the tangent is different, right? So it's a family of, it's a collection, or that's why you call it a bundle. So family of vector spaces parameterized by another space X, right? So this is this tangent space, right? So we can call this as a tangent space. So these are some terminologies I wanted to introduce, right? So we've seen some terminologies, and specifically we've seen some cases where they apply to physics today, like topological invariants, like how I said, knot theory, and things like that are already been used in physics. But these are pure math topics that will you might find useful in your future if you're doing theoretical work. That these will definitely come into the picture. The terminology you might start seeing. Okay, so it is definitely useful to know the language of these mathematicians.